trying to see if they can get these systems to work properly. And I want to, point of this talk is to educate a little bit on what are our challenges and how do we describe how we're going. Because there's a lot of news out there, and right now it's right and proper that we're working very hard on it, but at the same time there's a lot of hype. No surprise, you're probably used to that. And I want to try to separate out what's going on with the hype and really describe what's going on. And the central message I want to get to you is, although you hear a lot about people building systems and the number of qubits, you'll read this in the news, as important or more important is not just the quantity of the qubits, but the quality of the qubit. And for example, when you get to 50 qubits, which is what we're trying to build right now, 2 to the 50 is kind of the size, let's say, of the memory of a supercomputer. And by the time you get, I'll give you the example of 333 qubits, the parallel processing is 2 to the 333. It's about 10 to the 100, or a googol of processing power, which clearly is good for marketing our project in my company. Okay. Now, this is great, but this is for idealized qubits, theoretical qubits, not something you get naturally, and I have to talk about that. And also, you know, when you do run this through there, you still have to measure this, and you only get n bits, 50 or 333 bits of output. And you don't have access to all that parallel computing output. So what it means is you have to devise very special processors to take advantage of this, and that means it's a special purpose processor. You can only solve certain problems. Do something called a quantum supremacy experiment to demonstrate the power of a quantum computer, and we also think there's going to be useful algorithms where we have a modest number of qubits and a pretty decent error rates down in this regime here. There's a lot of speculation there. We know one algorithm. We have to find more, but there's some hope that we can do stuff here. And then once we start doing something useful, we should be able to accelerate our development and move here and do full quantum computation. As electrical systems, they're actually electrical microwave oscillators at about 5 gigahertz oscillation frequency. So this circuit, the light is basically aluminum, and the brown is where the aluminum has been etched away. You have a big ground plane, and you have capacitance of the central island to the ground plane. And down here are these called the Josephson tunnel junctions that basically represent inductors, nonlinear inductors, that form a nonlinear inductor capacitor resonator that forms our qubit. So these are nothing but microwave resonators. By putting in current through this line here, we can change the frequency of this resonator by between, let's say, 5 and 6 gigahertz, roughly. And these are designed with materials and at low temperatures using superconductors, so that the quality factor is about 1 million. So it'll oscillate for 10, 30 microseconds before they lose information. We can run algorithms. Here's a problem where we look at a graphene sheet, and we want to know the quantum energy levels versus magnetic field from 0 to about 10,000 Tesla. This is a nice problem that could be mapped on our processor that gives a very complex energy spectrum. Theoretically, this is something you can compute, but when you actually run our quantum computer, the results are given by dots, and you see, even though this is a very complex system, the experiment actually tracks what you would expect. So we can calibrate and run, and really get data that's good enough. This is probably good enough data that if you were trying to investigate a new material, you would get enough information from this to kind of get a sense of the material has the right properties or behaving in the way you were. We're in the quantum AI lab, so we're very interested in whether we can run optimization algorithms, which is essentially at the heart of when you do machine learning, and really help with doing that. There's some interesting ideas there and models, but nothing has quite been proven yet. And maybe, you know, since you know that machine learning, a lot of things are just empirically found and proven, maybe that's not the right approach. So we're working on that. But I want to talk about an application where we know what the algorithms are, and we know that if we can build a machine, this will make an impact. And this refers to you. And it's the idea that we're going to use a quantum computer to solve the quantum mechanics of materials, of molecules, or maybe other complex materials to get the information. You know, about 20–30% of all supercomputer usage is for these kind of quantum physics problems. And what was nice is Feynman in 1982 actually proposed using a quantum computer to map these quantum problems onto the quantum computer and then solve them properly. It's down a little bit more right now. At Google, we built this 72-qubit chip. Unfortunately, it's still in test, so I don't have anything to do here, but we're really pushing to get these kind of numbers at 72, in which case we can really start doing some interesting calculations. And hopefully in the next months or year, we'll be able to talk about that and show some good results. But this is work in progress, of course. So thank you very much for